Good morning. Today we are going to be looking at influence lines and its applications. Okay. So today's last time I had given you a problem and I had given you the answers, and today we are going to take up on that same problem and work through it. And then I will look at how to apply. That will be the last problem that I'll look at, and then we will see how to apply it for various. What is the application of influence lines? We now, hopefully at the end of by this lecture, we know what to do with influence lines, but therefore we are going to be looking specifically at the applications. Know how to use where do we use it? Okay, so let us go back to the problem that we were looking at. This is A, this is B, this is C, and this is D. We know the qualitative. I'm only looking at the quantitative, and the quantitative is the center point of the VE. Okay. Now for that, this is I, and this is I. This is 3 and 4. This is 4 and this is 4. Okay, and the vertical load goes from B, C, D. Okay, so therefore if we look at it, what's the first step? And by the way, we had drawn the influence line for this. I'll just put it together for you. If you remember this one, this, and I'll draw it using red. Where this theta and this theta are the same, and this one of course will go like this. We don't care. This is the influence line for VE. Okay. Now, as the load proceeds from B to C to D, let us see, when the load is between B and C, you set up a fixed end moment at BC and CB, and then when you go from C to D, you set up a bending moment at C and D. Okay, so therefore we have to tackle three problems. DC we are not going to tackle because it's a fixed end, and the fixed end moment DC is going to land up being there. So it's not going to be a moment distribution, but we need to do 3 sets of moment distribution, and I'm going to do all 3 sets together so as to the first set is here, the second set is here, and the third set is here. The first set, let me put, this is going to be AB, and there are 3 of them, BA, BC, CB, CD, and then DC. Okay, then again this one is going to be the same, AB, BA, BC, CB, CD and DC, and finally the last one AB, BA, BC, CB, CD and DC. Okay, in this particular case we're going to first tackle plus 100, 0, 0, 0. In the second case we're going to handle 0, plus 100, 0, 0, and the last one we're going to handle 0, 0, 0, plus 100 and 0. These moment distributions we have to do for fixed end moment at BC, CB and CD. The DC we don't need to do because that's a fixed end and it's going to show up directly at DC. Okay. Now the distribution factors, both of them are continuous. So you're going to have I upon 5 and I upon 4. So I upon 5 and I upon 4 is going to give you, this is I upon 5, this is I upon 4. This one is going to be I upon 4, I upon 4. So it's going to be 0.5, 0.5. And this is going to be 1. This is going to be 1. Okay. So this 1 here, next one. Here, same thing. 0.44, 0.56. This is going to be 0.5, 0.5. 1 here, 1 here. 0.44, 0.56. 0.5, 0.5 and 1.0. Okay, so we know, and there's going to be carryover in all the directions, so we know how this entire thing is going to happen. So this moment distribution, I'm not going to go into the details, I'm just going to put down some of the numbers so you know how to look at it. Minus 44, minus 55, and then this is cancelled. Here you get minus 22.2, here you get minus 27.8. So this 27.8 gets distributed 13.9, 13.9. This carries over here to 7.0. This carries over here to 7.0. This gets minus 3.1, minus 3.9. This gets carried over to minus 1.6. This gets carried over to minus 1.9. And then this gets done as plus 0.9, plus 1, and we'll stop there because we've reached less than 1% and close it at this point. Okay, and so this becomes minus 23.8, this becomes minus 47.5, this becomes plus 47.5, this becomes minus 14.9, plus 14.9 and plus 7.5. Okay, then similarly we do it for this. This is going to be minus 50, minus 50, break, carry over, minus 25. Now minus 25 gets done with plus 11.1 and plus 13.9, correct. This one comes as plus 6.9, this goes as plus 5.6, this comes out as minus 3.4 minus 3.5 minus 3.5 goes as minus 0.17. Then we come over here. This is minus 1.7, so this becomes plus 8 plus 0.9. This carries over to plus 4. We close it here, and by the way, this I've just done the. So this becomes plus 6. This becomes plus 11.9. This becomes minus 11.9. This becomes plus 53.5. This becomes minus 53.5. And this becomes 26.7. This one goes exactly the same way. Minus 50, identical. This goes minus 25, plus 11.1, plus 13.9. This carries over to 6.9. This becomes minus 3.4, minus 3.5. Carry over 1.37. Here 1.7. This carries over. This becomes 0.8 and 0.9. This carries over 0.4. Close. And this becomes plus 6.0 plus 11.9 minus 11.9 minus 53.5 plus 53.5, 46.5. This is 46.5, and this becomes minus 26.7. Okay. Now all of these, these are, I'm just doing it, that essentially we are writing down that MBC is equal to, see, we are not interested in AB and BA because the load does not travel on AB and BA, and so those are always going to be equal to 0. Okay, so we are only interested in the ones that where the fixed end moments are non-zero. So we have 0.475 MBC minus 0.119 MCB and then minus 0.119 MCD. Then we have MCB is equal to minus 0.149 MBC plus 0.535 MCB minus 0.465 MCD, and MCD is equal to 0.149 MBC minus 0.535 MCB plus 0.465 MCD, and finally MDC is equal to 0.075 MBC minus 0.267 MCB minus 0.267 MCD plus MDC. This is the fixed end moment at DC. Okay, so having these are our expressions, these we get, and once we get these, you see MBC and all these numbers I know directly, right? Because MBC is equal to, when 0 is less than x is less than 4, MBC is equal to 4 minus x. Squared into x all upon 4 squared. That is MBC. MCB is equal to x squared into 4 minus x upon 16. okay, and MCD and MDC are equal to 0. When you have between 4x and 8, MBC and MCB are equal to 0, and MCD is equal to 8 minus x the whole squared into x minus 4 upon 16, and MDC is equal to x minus 4 squared into 8 minus x upon 16. Okay, so these are the fixed end moments, and now we need to do what's the next step. Once we have figured out from the moment distribution the relationship between the member end moments and the fixed end moments, we also have the expression for the fixed end moments while the load is traveling from B to C to D. Okay, and now finally what we have to do is we have to write down all the expressions for it. Okay, so if we look at it, now the only thing that we are doing is VE. Okay, so understand that we are only interested in VE, and if we look at it in terms of, let's say that the load is between 0x and 4. Okay, then one of the things that we do know, let us look at this. This is MBC, this is MCB. Okay, in addition we have the load 1 at a distance x. Okay, so therefore if you look at this one, I'll call it as VBC, and I'll call this as VCB. Okay, so if you look at this in this way, VBC is going to be equal to 4 minus x upon 4. Okay, that is from this part, and the other part is plus MBC plus MCB upon 4. Okay, and VCB is equal to x upon 4 minus MBC plus MCB upon 4. Okay, once we know this, now our E point is here. So this is our E point. So when 0 is between 2 minus, that means the load is between B and E. That is what 0 to 2 minus means. That means if you look at it, the shear force, by definition, if we make this cut, we'll have this, we'll have this, and this is VE. So if you look at it, VE is going to be equal to VCB. And when the load is between this, VE is equal to, you will see that the other side, when VE, you will see that this is VBC and this is the positive VE. So this is going to be minus V. So for this, V is equal to this, and for this, this is. Now this is what, these are the expressions for VE when the load is between B and C. We now need to just find out what is going to be the VE if the load is between 4 to 8. So when load is between 4 to 8, then BC becomes MBC, MCB. The load is no longer there, so we have VBC and VCB, and we see that VBC is equal to MBC plus MCB by 4, and VCB is equal to minus of MBC plus MCB by 4. Okay? And if we look at it, then VE is equal to minus BC, or which is also equal to VCB. Okay? So we have these expressions, and if you look at it, then by the way, this here MBC, this is minus and this is minus. Okay? So now let us look at how to compute. Now what we do is we compute, and for computation again we draw this. We're going to have X, then we're going to have MBC, MCB, then we're going to have, who cares, we don't need MBC, we need MCD. We get small m and capital M and capital, then we get VC, and then finally we will get VE. So this is X, this is M, the fixed end moment, this is the fixed end moment CB, this is the fixed end moment CD. We don't need anything else for MBC and MCB because VE only depends on those. VBC, VCB and VE, and what we have to do is 0, 1, 2 minus, 2 plus, 3, 4, 5, 6, 7, 8. So let us draw these lines. Why 2 minus and 2 plus? Because when the load is just to the left and just to the right of the E, the shear is different, which we've already computed. Okay? So having done this, just substitute X, we get this 0, this 0, this 0, this is 0, this is 0, this is 0, this is 1, this is 0, and this is 0. This is the expression. Then for 1, we compute, and this becomes 2.25 by 4. This becomes 0.75 by 4. This is 0, because MCD is 0 when it's 0 up to here, up to 4. And MBC and MCB are 0 when between 4 and 8, because this is also 0 at this 8. Okay, so when we compute, we get it, we get this becomes 0.290, substituting these. MCB becomes minus 0.184, so VBC turns out to be 0.7765, this turns out to be 0.2235, and therefore VE is 0.2235, because up to 2 minus it is equal to VCB. Okay, then we plug this in, this becomes 2 by 4, this becomes minus 2 by 4, so when you compute this becomes 0.297, this becomes minus 0.342, so this becomes 0.488, so this becomes 0.5112, and so this is now 0.5112. At this point 2 plus, all of these are identical because the moments cannot change, VBC also is the same. But now at 2 plus, VE is equal to minus of, so this is going to become minus 0.4888. Okay? And then this becomes 0.75 by 4. Now you keep putting in these values, you will get this is equal to 0.156, this is equal to minus 0.329, this becomes 0.2068, this becomes 0.7933, so this becomes minus 2068. This, I mean, I'm just putting down whatever the values that I had got last time. Okay? At 4, all of these are 0. Now here, this becomes 2.25. This is 2 by 4. This is 0.75 by 4. Substituting those in, we get minus 0.067 minus 0.060 minus 0.022. This is of course 0, 0, 0, 0 and 0. Here once we substitute these, we get minus 0.0823. This becomes this one is 0.262. This becomes minus 0.0823. This becomes 0.08, and so this is plus 0.0823. Okay, this one is minus 0.233. This is minus 0.087. So this becomes minus 0.733. So this becomes plus 0.733. This one is minus 0.0273, so this becomes plus 273. These are the numbers that I had done, and so I just evaluated the procedure for getting these. Okay, so I think by now you know the steps. Okay, and I'm putting it down for quantitative influence lines. First, identify load path. Identify which fixed end moments come into play. Okay, when you know the load path, you know exactly from where which fixed end moments are going to be non-zero as the load moves from whichever point to whichever point we want it to move. Okay, so identify which come into play. Then for each FEM equal to 100, do moment distribution. Okay, so as many number of points at which you develop fixed end moments, you are going to get that many moment distribution. For example, in this particular case, we had, when it was between B and C, we had BC and CB operating. When it was between C and D, we had CD and DC. Now DC was a fixed end, so we did not need to do a moment distribution for that. But for the other three, BC, CB and CD, we had to do the moment distribution. Once you do all of those, then you get member end moments, okay, Mij in terms of fixed end moments. Now find expressions for fixed end moments as load moves. Okay, so in other words, for each member that you have, you put it at a point X and you find out the expressions for the fixed end moments. Once you find out the expressions for fixed end moments, you get the expressions for Mij as the load moves. And then do equilibrium, or should I say use equilibrium to compute any response quantity in any member in terms of Mij and unit load. Okay, so once you do that, then you've got it, and then you can put in different values of x and evaluate whichever response that you need at that point, and that gives you the influence line for the particular response quantity. For example, in the problem that I've just done, the response quantity of interest was VE, and so therefore we only obtained the expressions for VE in terms of MBC and MCB, and when the load was in BC also in terms of the load. When the load moved away from BC, then the load did not come in, it was only in terms of MBC and MCB. Okay? So much for how to get influence lines both qualitatively and quantitatively for any structure, be it statically determinate. In the statically determinate structure, the Müller-Breslau principle gives us both the qualitative as well as quantitative, because whenever we remove the restraint corresponding to the response quantity of interest, a statically determinate structure becomes a first order mechanism, and all displacements are straight lines. And therefore, we don't need any method. We also get the quantitative. When you have straight lines and you know the end, you always can find out anything, as we have already seen. So the Müller-Breslau principle gives us both the qualitative as well as the quantitative for a statically determinate structure. For a statically indeterminate structure, we can still continue using the Müller-Breslau principle, but it only gives us a qualitative sense of the influence line. To get a quantitative sense, you have to go through the direct approach, in which you have to make each member into statically determinate and then solve for it. Okay, and that is how to make it statically determinate. Okay, so much for influence lines. Now the questions arises, see, up till now whatever we've done, there has been a reason for it. Okay, this is the first time I looked at a problem and I said, look, let us first look at the influence line and then we will see what the applications are. So right now I'm looking at where do we apply influence lines. You see, it's obviously moving load. Okay, what kind of moving load can we have? You see, one of the kind of moving loads that we can have is something like this. That over some A, we have some load intensity which is given uniform intensity PA, so that the total load is P into A. When does this kind of a thing happen? This happens when you have a truck. Okay, when you have a truck or a car traveling over a bridge, this is the kind, there is an area over which the load is distributed. On the other hand, you may have a situation like this, effectively point load, where you have a load which is P. This is capital P, this is small p. So load is P and it's acting at a particular point. When can you have this kind of a thing? Okay, this can happen when you have a train on a railway track or a crane. Essentially the load is transferred through a steel wheel which has in a sense a point contact. Okay, so these are the two kinds of moving loads that we have. So how do we tackle this? Well, you see, the overall point here is this. Let me just take this particular example that we have just done to look at it. Just 1 second, I'll get it. Yeah. We have this influence line, right? And now we know the values also. This is 0.511, this is 0.489. Okay. What does this do actually? This tells us that to get the maximum value of VE, which is the position of the load that we have. So this is the position that just for maximum value of VE, we need to put it just to the left. So x equal to 2 minus is VE max, and the value for a unit load is equal to plus 0.511. When we have this, for this load, this moving, we know what the maximum VE is going to be. We know where the load has to be applied. It has to be applied at this point, and once we apply the load at this point, you can do an analysis and you can get that VE max is equal to 0.511 P. You see, I mean, I'm just giving you the example VE, but this you can do for anything, any response quantity. For example, what is the maximum support reaction? We know what the maximum support reaction is. We can also find out the position where it is. We also know what the maximum value is for the unit load. So when you have a train or a plane, all you need to do is whatever value you get for the response quantity, you multiply it by P. And that's it. So this, when you have a concentrated load, finding out the maximum value, see, when you have a moving load, you can never find out. That is the reason why we have influence line. But now we know for a point load how to apply the influence line to get the maximum response for a given point load, moving point load. What happens when you have something like this? Well, this gets even easier. Let me look at this more. So let me look at VE. So I have VE, which looks like, I'll draw it, this and this. I'm illustrating with VE, mind you. It's not as if I'm choosing. So this is 0.511 and this is 0.489. This is what we have evaluated, and then we have evaluated for every point. Now the point here is, if we have a load which has a particular pressure over a particular area, this is a typical class AA loading, 70R loading. If you look at the Indian Road Congress Code, IRC 6, you will see that you are given this kind of a load. Of course, what you are given is many loads together, okay? But the point that I am trying to make is that once you have for one, you can always place it any which way you want it over, because once you have the load one position, you have all the other load positions automatically. Now the total load P is equal to PA. How do we solve this problem? Okay. See, note that all we need to do is find out for this load what the maximum. We need to find out the position. Which position do you think is going to be the position of the load? Automatically, if you look at this, you will see that this is the maximum. So automatically, one edge of the load should be here. And if the load sits like this, you will get the maximum influence of the load on VE. So therefore, what we do is, we know this A, this is A, and what we do is, we find out the area under this curve. So the area under the influence line over the distance A when the load is placed at the maximum, okay, over dx multiplied by P gives me, see, this is the pressure. So this pressure multiplied by the influence line, okay, gives me the pressure at this point. And then when we integrate it, we get the VE max for this load. Okay. How do we integrate? We actually don't integrate it. Okay. What we do is we discretize it and then numerically integrate it. You've got your VE max. Of course, what might happen is that you might, once you place one load, the other load may come here. All you need to do is sum up influence lines. Once you placed one load at the maximum, the others will come automatically. You know, the distances are fixed. Okay, the wheels, the axles, loads are fixed. So you can always find it out. And this way you find out VE max. Of course, I'm illustrating it with VE max. Okay. So therefore, you see now how for a given moving load, how do we get the maximum maximum response. In this particular VE, we could also do it for RA, RD, MD, MA, anything for this particular problem. For your own particular problem, you can always solve the specific problem and find out its effect. This is the reason why it is actually an analysis problem. You know, we are actually trying to find out what? We are trying to find out the maximum value of a particular response. Base shear, shear force at a particular point, bending moment at a particular point, the reaction at a particular support, the moment at a fixed support. Okay, these are the things that we are interested in. And so whatever we are interested in, we draw the influence line for that. And then for what we always do is this, that whatever load you have, you always place the load where you get the maximum influence. So once you place the load at the maximum influence, if it's a point load, the value of the influence value multiplied by the load directly gives you the maximum value of the response under the moving load. And then if you are doing for a distributed load like a tire load, then this is the procedure that you use. Okay. So in essence, the overall use of influence line is 1 to determine the position of the load. Determine the position of the load wherever influence on the response. That is the reason why we call it influence line. Influence on the response is maximum. Okay, and once we determine the position, if point load, then response, design response is equal to influence line into load. If distributed load, then design response is equal to integral over the distribution area or length into influence line into pressure into dx, where P into A is equal to. So basically P is equal to P upon A. That is the pressure. And so therefore here what we do is load upon A multiplied by influence line over the length A, you integrate it. Okay, and that gives you the design response. Okay. So this in essence is what overall this thing is. Now just to ensure that I leave you with some problems to do, I'm going to give you 2 or 3 problems to do for your own self. I'm going to define one problem. This is the same problem as what I've just done. In this problem, this is my E point now, which is 2 meters. Identical, it's the same problem in fact. 4m, I, this is 3, this is 4, this is 4, A, B, C, D. Okay? And I ask you to find out this array, okay? The shear VE and the bending moment at B. Quantitative influence line for bending moment at B, R at A, and V at E. Okay? You find these out. I've already done this. I will give you the answers for your computation. If you look at it, this is going to be, this is x 0, 1, 2, 3, 4, 5, 6 minus 6 plus 7, 8. RA, VE, bending moment at B. This is going to be 1, 0, 0. This is going to be 0.785 minus 0.038 minus 0.294, 0.503 minus 0.073, and this is going to be minus 0.30. For 3 it is 0.219 minus 0.71 minus 0.161. For 4 all these are 0. For 5 this is minus 1, this is 0.62, 0.0383. At 6 we have 0.125, this is 0.399, 0.095. 6 plus, these two remain the same. This one is minus 0.061. For 7, this is 0.078 minus 0.313, 0.060, and ultimately 000. I've given you the answers. You have to solve this problem yourself. Okay? And then I would like you to find out the maximum values for a point load of 100 kilonewtons. Okay? So you find out the maximum value or the design responses for all these three for 100 kilonewtons. Okay, I am going to stop here. I hope that the lectures on influence line has given you a little bit of an insight on how to obtain influence lines for structures and then how to apply them for actual problems to be solved. Thank you very much. It's been indeed a pleasure interacting with you, and I hope that my treatise on the force method, the displacement method, and then the matrix flexibility approach, the matrix displacement method, the moment distribution method, and finally the influence line has given you some idea of structural analysis for statically indeterminate structures. Thank you very much. Bye.